Okay, welcome. Good morning, everybody. Welcome back to the second lecture of the second week of the Intelligent Systems course. In total, there's 6 of the 12 lectures. So at the end of this lecture, we are half through. In terms of the new material, I think we are a little bit more than half through, but there's still quite some stuff to come. In a way, this is a sort of an intermediate lecture, I have to say. And it's for me, it's also a new lecture, so I'm a bit curious how this will work out. Because what I'm trying to do today is to apply the logical mechanisms, the logical formalisms, as I discussed them yesterday, particular propositional logic and first-order logic, to the game of Schnapsen and the practical work that you have to do. And part of it will be trying to do some class exercise and to see whether we can come up together with some interesting ideas and solve them on the board. So I'm not sure whether we manage, so let's try. So today's lecture is about modeling decisions problems in logic with a specific application to the practical that we are working on, namely an intelligent agent for playing Schnapsen. Obviously, the technology works for other problems as well, but I will focus on this specific application. So the plan for today is decision-making with logic. And how are we going to do this? I will first introduce a little bit the idea of a logic as a decision procedure in the first place. Then I will show and practice with you a little bit how we can represent information about a game, about game states, background knowledge in games, in first-order logic. And then comes a sort of trick of translating this back into propositional logic, because in the end we want the propositional logic prover to do the reasoning for us. I will introduce how this reasoning works, so what's underneath the hood in a reasoning engine, which is the Davis-Putnam. And I always forget the 2 other names who have helped develop this Davis-Putnam algorithm. And then I will talk at the very end, I will also talk a little bit about the final project, because you have now reached a state where you can start thinking about doing research, and I will help you a bit to sort of get going there. So that's my plan for today. It's less structured than the last lectures, because I want to practice some things in the middle, but still this is the sort of the main idea of what we're going to do today. There will be 3 different types of knowledge and things covered today, and the one is on the theory side. I want to give you a very, very brief introduction in theory of computation. And that is because I want you to understand why on earth are we using first-order logic for modeling and propositional logic for reasoning. It sounds really weird in a way, if you understand a little bit. So I want to briefly explain why this is the case. And I want to do this by giving you a tiny little background of the theory of computation. A related, very similar thing is the general problem of knowledge representation, namely how to find the right formalism for the right problem. And this is a very typical example where we face exactly this challenge of finding the right problem for the right task. And I also want to mention this. But there will also be practical things, namely helping you model some strategies for playing a game, for example, in the logic. So how can we use this then for the game, which will also help you with the worksheet of the second week, which will be published today. And but there is also some algorithmic stuff that I need you to understand, namely closed normal form, how to calculate closed normal forms, what is a closed normal form, and the idea of propositionalizing. So how can we come from a first-order logic formula to a propositional logic formula that is equivalent in the sense that it is entailment preserving, so that you can derive the same things with these two different formalisms. So there will be a bit of technique, there will be a bit of theory, there will be a bit of practical today in today's lecture. So it will be slightly different than the other ones. First, I want to start with doing some other matters. One thing I want to sort of apologize up front with, and that is that I have the very bad habit of not caring too much about syntax when I talk about formalisms. So you will see me write something like this. Which all means the same thing to me. It's all one thing, namely it's a negated atom. And it's just a choice of negation operators in my language of choice when I talk about it. And this is, I have no standard nomenclature for this. The same is for a formula such as A or B. You will see me also write it down as in any of those ways. There is nothing magic, it's just a different way of writing the same thing, and I simply can't make up my mind up what I want to, which one I use. And for different programming languages, you need different things. So in some of the examples, you will see this operator, the tilde operator for the negation. In some of them, you will see this negation sign. But when I'm not in LaTeX and I have to simply want it in text, then I would probably use this one. So you have to bear with me on this one, and you always have to, if this is unclear, please ask. Also in the exam, I hope things will be clear enough that you know that this is, we only have these operators, we have, and there are different ways of writing them up.
Which one did you recommend for that?
Sorry?
Which one did you recommend for that?
This one is if I have, this one is the sort of the nicest. I like most, but you need LaTeX to write it.
/neg.
Yeah. So, but as I write most of my slides without LaTeX, I can't be bothered to write the LaTeX. So I just, and in Word, this one looks ugly and it takes a bit of an effort to find it. So I usually don't bother and I write this one or I write this one. I just want to apologize up front, and I want you to know about this so that you're not confused when you see all these symbols. There's really nothing special here. Then the second thing, in other matters, I haven't written down anything, but I really want you to tell me now whether there are things that need to be addressed or whether in principle everything works according to your expectations, or is there anything we should do differently to improve the experience you have in the course and the learning that you can perform? So I've tried to set the every day to push the videos of the lectures for you to watch. I also try to push the slides. If I forget to push up the slides, please just send me an email and I will do as quickly as I can. The working groups last week, from what I heard from Dalia and from Denise, I think they worked fine. So I also enjoyed mine. So I think the questions were relevant. These are the questions that are similar to the questions of an exam. There was an exercise exam put online, which allows you to get some idea of what kind of questions you might expect. So if you have any suggestions, please let me know. Did you all get access to support, computer support, when you needed it? So did it work with the computer assistants? Yeah?
I have a question about the code. So we only have the TA slots to ask questions about code, right?
Yes.
Okay, so
Yeah? Okay. So the question was, is there any other way of getting help with the code apart from the TA slots? And obviously the TA slots are very short, so if you need more help, you can always make appointments with them or with Paola in particular to help you in more detail. Also, discussion group is, I think, a good place to start it. And if that's not enough, we have to think of something. Yeah. Okay. One thing from my end, I noticed that there are still groups of 2 people and groups of 1 and single people floating around. And we have to make sure that there are no individuals not being able to find a group. So can you please, if you are still a member short in your group, post an announcement and try to find someone to become the 3rd person of the group, and vice versa. If you're on your own, post on the discussion board so that you find a group. We have to sort this out this week. There's no harm done yet if we have this week not sorted out the groups, but from next week on, we really need to get the groups, because it's now time to start thinking about the research that you want to do in the last couple of weeks. Are there any other matters you would like me to take attention to now? No? Okay. So then let's start with the part on decision making and game playing with logics. And in this case, there are obviously many other logical formalisms that might be even more suitable for these kind of decision making processes and games. There are also, there's, for example, a programming language that's based on these logical representation mechanisms, Prolog, that might be much more suitable to be integrated in your as a game engine. I leave that apart. I really want to use the most simple and most standard and well-established representation formalisms, first-order logic and propositional logic, for you to model. So, and it will be good enough for you to see that you can express in principle most of the things, or many of the things that could be interesting for such a game. So until now, we've been looking at the principle of rational agents, so agents that try to play the game by optimizing their chance of winning, so making some estimation or some criteria, setting some criteria for winning a game in the game scenario, and then trying to come up with a strategy to really win a game, maximizing your chance or optimizing your chance of winning the game. We did this by a state space representation, so every situation that we were in a game was an abstract space, and the moves that we can make in the game bring us from one state to another. So we have many transitions that we can have between the states. And then the question is, if we have states that fulfill the goal conditions or the winning conditions of a game, is there a path in this state space representation that gets us from the initial position where we are at the moment to one of the winning states? And that was what we basically spent our time last week, namely by search, having systematic search algorithms, some with informed search, where we had information about the games formulated in heuristics. And in the game situation, you usually have an opponent, so you try to take the decisions that your opponent makes into account. And then we run into the point at the very end of last week. Then we have, in a game such as Schnapsen, we have imperfect information. And that basically leads to the fact that we do not know anymore, relatively soon, in which of the states in my state space representation we end up after one or two moves or transition. So this is a situation that we face when we apply the systematic search through the stage space. We have maybe 5 cards. We don't know the cards of the opponents. We might want to use some kind of min-max search, but already in the second stage, we need to take into account the full uncertainty of the possible choices of my opponent, and already on a relatively low level, a high level in my search tree, there's so much uncertainty that the systematic search doesn't work anymore. So that was the bad news about the Schnapsen phase 1. I mean, you should all be aware now that Schnapsen phase 2 is relatively simple to address because you can systematically look through all the options using a min-max and an alpha-beta pruning algorithm. But in phase 1, it simply all explodes. So the current suggestion at the end of last week was, let's apply some Monte Carlo sampling, so simply randomly go through possible gains and average over the possible outcomes. So basically we pretend to play a card, ace of spade, and then we do a random choice of what would be the possible cards that my opponent could have, what are the possible choices that are in the pile. I make a choice randomly, and I play a random game, either a random game or I play a game until I can make a full alpha-beta. So I play until the end of phase 1, basically. And then I do this many times, so that at the end I can average over the different games that I've played randomly on the basis of the decision to play this card. And then I do the same with all my 5 cards. I average over possible games that could be played. And then I take the one which has the highest chance of providing a winning game. So this is relatively brute force, and as we do not have any information about the choices that we make, we just make it randomly. So it seems that we can do better. And in a way, we have, I think, RDeep is the bot that implements more or less this strategy. And we have an attempt to do better, the bully bot, which implements some of the human strategies, and probably some that are relatively difficult to beat, actually. So I don't have an overview of, have you played experiments between random RDeep and bullybot? Anybody? So is that a clear winner between the two? Yeah. Okay. Okay. So this works for the complete game. The situation is there for the phase 2. The point is that the situation there is a bit different because we don't have, our random choices are not that important to do. And in the first phase, we can't even apply min-max. It will never finish. Yeah.
Of the 3 default bots that were given to us,
yeah.
What was RD did best. They came bully,
okay.
And they came red, except before the bug with mismatches was fixed. At that point, bully actually was the worst player possible.
Okay, so let's not discuss the situation before we fix the bug, but only after we fix the bug. And I can imagine that RDeep, so this method of perfect information Monte Carlo search, worked better, I don't say pretty well, but it worked at least better than the informed, the more informed, more humanly informed bullybot. The idea is now that we look into more detailed and more sort of more rich ways of defining human strategies and integrate them into the decision making of the bots. So at the moment, the bully bot, I think, has 4 different things that it checks. So it might play a wedding first, it might play a high card, an ace first, and some of these strategies might be you might agree with, some of them you might not. But what we will show, or what I want to discuss today here, is that there is a way of representing those strategies explicitly in a logical formalism and integrate them into the decision process of the bots. And what kind of strategy can we apply? We can use game-specific knowledge. So for one specific game, we know, for example, that if the ace and the 10 of one color has already been played, then the king is a high card. Or if I have the 10 and the ace, so if it's known where the ace and the 10 are, then I have the king, which is the highest card, which is cheap. So that is a valuable information for me to play the king, because then I know that chances that I get the trick are very high. While if someone else invests a trump, my costs, the risk is very low. So it's a lower risk, high gain strategy. You can also have a sort of global information, namely that an ace and the ace of spade is always something expensive because it gets 11 points. You don't want to lose an ace. So this information really can help you to make heuristics explicit so that you can build a bot that doesn't make the mistake of playing randomly, for example, the ace of spade. This is, I think, the ace of spade, isn't it? Not the ace of spade. Clubs. So the ace of clubs, that would avoid you to play this card because you know that if I lose it, it's an expensive card that would be a bad move. So that basically you come up with the strategy, you define, I don't want to play expensive cards in phase one. I'm now talking about phase one of the game, where the opponent can always trump, if he has a trump or she. So the strategy might be not to play a valuable card. But for that, you need to know what a valuable card is. And this is what we're going to look into about now. So how are we going to do this decision-making in biological reasoning? In this specific case, we represent the necessary knowledge in some sort, sorry, this is a generic idea. We represent the necessary knowledge in some suitable formalism. And that's a choice you have to make. It's a typical knowledge representation challenge to find the right representation mechanism. And then you model the environment knowledge, and you model the knowledge about the specific state you're in. Because we're still in this state-space framework. So you model the state, the relevant information of the state, and you model the environment, where the information about the environment, you only have to do once because it holds for all the states, and then you have to add the information that's specific to this one state to your logical inference machine. And then you represent this decision problem as some kind of reasoning problem, such as an attainment problem, in a suitable formalism. And they don't need necessarily to be the same formalisms as long as they get the same results. And then you make logical reasoning, such as calculating the attainment, and that is then gives you a correct or a good strategy so that you can act upon that. And for our implementation now for the intelligent agents for the second week, the choice is to use first order logic as a representation mechanism, and then we translate it into propositional logic by propositionalizing into propositional logic for reasoning. That's a sort of an arbitrary choice that we have made because for some reasons that I want to talk about now. And to do that, I need a tiny little bit of theory of computation. And in order to do that, I use my favorite slide. And this is a slide that I show at every course that I teach, more or less, I think. Maybe not much in data, I just remember. Anyway, so you might not have seen it, but who knows who this guy is? Yeah. So this is Alan Turing, and I show this slide because I always, this is my moment, my 25-minute break, not after 25 minutes, maybe even after 25 minutes, because I always want to talk about Alan Turing during my lectures, because I think he was one of the most important figures of the 20th century for various reasons. So I guess you've all heard of Alan Turing. So you know that he's one of the persons who started thinking about the notion of artificial intelligence, came up with a way of defining what does it mean for an agent to be intelligent, which might be the smallest of his feats. What might be least known is that he was a great mathematician and logician. He's most famous probably for the work that he did in helping to decode the the cipher machines from the German Navy. So he really had a societal impact by helping to end the Second World War earlier than it would otherwise have ended. Mathematically, he showed something which I will talk about in a minute. So the question of is it possible to develop decision procedures for all problems that you can somehow formalize? So that's my theme, why I bring up this slide. But the last thing, because why I want to talk about him is that it is believed that he killed himself because he was heavily disqualified for his sexual orientation and for not being as the norm in Britain expected someone to be. And I think it's one of the most horrible examples where people, one of the greatest geniuses of the 20th century was driven to death because we as a society didn't accept other people to be as they are. And so I always want to make this part of the sort of the tribute to Alan Turing, that we should always respect other people as they are and give everybody the room to stay, because this makes science, even if it's the smallest of all the things, it makes science better, because we all have to be our sort of in our own way contribute to this field. And this is my sort of small contribution to tribute to Alan Turing. Let's all accept the diversity of all of us. So the work that he did was in mathematics. So that was before he did the work on deciphering in Bletchley, was on decision problems. And the problem of decision problems is basically you have a problem that you want to solve, and you have an algorithm that somehow tells you, yes, the answer is true, the answer is false. And the question is, can you find an algorithm that always solves these problems for given formalism? And what Turing basically showed before there was even the first computer around was that there are problems for which we can show that there is no algorithm to solve this problem generically. So the way he showed this was to build a mathematical machine called the Turing machine, which has it can do very few things, but it is basically complete. You can everything do with the Turing machine that you could do with a modern computer, although it would take longer. And what he showed was that there was a problem in that he couldn't solve with his Turing machine, which basically resulted in him showing that there are problems that cannot be solved, because he showed before that his Turing machine was universal, so that in principle it could solve all the mathematically formalized problems. So he basically showed the existence of undecidable problems. So you have a problem, you know the input, and you know that there cannot be a machine that gives you the answer whether the output is true or the output is false. So the halting problem was this example that he gave. So I spare you the details, but this is basically his contribution in one of his, I think it was his PhD thesis, that he showed that there exist these problems that can never be solved by a machine. So then, why am I bringing this up? Because this is very relevant for logic. It's one of the main problems that we as logicians deal with, is whether the question whether some formula is entailed or not by a knowledge base, whether we can write an algorithm that gives us the answer, yes, it is entailed, or it's not entailed. And basically, what was shown, or was an immediate consequence of the results of Turing's work, was that first-order logic is not decidable. So I can write down a formula in first-order logic, and there is no chance that an algorithm tells me that it's unsatisfiable. First-order logic is a special case. and you'll see later why this is a special case, because it's so-called semi-decidable. Basically, semi-decidable means that if a theorem is logically entailed, you can prove it. But if it is not entailed, we cannot prove it. You can think of it in the way that you can say, I can enumerate all the true formulae, all the entailed formulae, but I never know when the entailed formula that I'm looking for is coming. And it might be that the formula that I'm looking for that's not satisfiable will never come. I know that all the formulas that are entailed will come eventually, even if I have to wait for a long time. So it's a sort of enumeration-wise, I can decide everything that's true, but I can never show that something is false. So basically, this is the problem that we have with first-order logic. We have a formalism that's very, very rich and very nice to model things with. But in the reasoning, it can happen that we'll never get an answer to our question. And in practice, this is less of a problem than one might think. But still, it is. There are other reasons for rather not using first-order logic for reasoning. In particular, if we have this specific case where we know in our game, for example, where we want our quantification mostly to be over all the possible states, over all the possible cards that we could play, we know that our set of possible objects in the domain is relatively small because we only have 20 cards. So the universal quantification that I introduced yesterday says for everything in my domain, some property must hold. This is an open statement. It could hold for a domain that has billions of elements, and then the reasoning would be incredibly complex. But we know that in our quantifications, we always have 20 possible states, 20 possible cards to reason over. So that makes it relatively controlled and small, so that in that case, it is better to use for reasoning a language that works on this kind of level of concrete propositions about the world. And that is the reason why we translate our elegant formulas in first-order logic into propositional logic and run a propositional reasoner on it. So this is sort of a fundamental knowledge representation question. What kind of language do you want to represent your knowledge? And we use first-order logic as an elegant modeling language. But then what language to use for reasoning? And we use propositional logic as an efficient reasoning language. And this works because we know that we have a small finite domain, so we can translate first-order logic into propositional logic without losing entailments. And then we use a propositional logic reasoning. So another choice that sort of arbitrary we made was that I think the most intuitive logical reasoner that's around, automatic reasoning tool, is the Davis-Putnam algorithm. And that basically is a search algorithm through all possible assignments that you could give to a formula. So remember that we had a propositional logic. We could assign values true or false to our variables. And of course, what you can do is to say, okay, suppose you have a formula with A, B, and C as variables. You say, okay, suppose what happens if A is true, B is true, and C is true? Does it make my formula satisfiable? No, it doesn't. So I have to continue searching, and I do A is true, B is true, and C is false. And you go on. Basically, this is the truth table way of looking at things. And if you do this in a systematic way, searching through the search space, like we did last week, you can come up with a relatively efficient algorithm, and that's the Davis-Putnam algorithm. There are two technical things that you need to understand about this algorithm. I will get into detail about this tomorrow, but there are two things you need to understand already now. The one is that formulas have to be in closed normal form. I'll get to that in a minute. A closed normal form is a conjunctive normal form. So it's a conjunction of disjunctions, of literals, of atoms. the definition comes in a second. So it's a specific form of a formula that's equivalent to the original formula, but more efficient and more standardized to do the reasoning over. So that's number one. We need the formulas to be in closed normal form. And the second thing we need is it's a calculus that can only do one thing. And the only thing it can do is check for satisfiability. Is there a model or is there not a model? What we want, though, is we want to check for entailment. Yeah? Remember, entailment was that a formula alpha is entailed by a knowledge base if alpha is true in all the models of the knowledge base. So the assumption is that, or the way how this works, this entailment by refutation, is that you add the negation of the formula that you want to prove entailment for and show that it is unsatisfiable. So basically what you have to do in order to show that A is entailed by the knowledge base, we assume that A doesn't hold. And as we know that if it's entailed, it should hold in all of the models, there must be a contradiction. So basically adding the formula that is entailed, that we want to prove that it's entailed, negate it to the knowledge base and show that it's unsatisfiable is exactly the same as showing that the formula itself is entailed. Again, something I will spend a bit more time tomorrow, but this is a second ingredient we need when we do the modeling. So the first one is our formula have to be in propositional logic. The formula have to be in closed normal form, and we need to add the thing we want to prove to be entailed in a negated form to prove with Davis-Putnam by refutation. We'll see in a minute a little bit more how this works, but these are the big three ideas. So what's a closed normal form? So that's one of the sort of technical things you have to really understand and have to be able to do. I guess this was also done in logic and sets, so it should be familiar to all of you. But still, let's spend a little bit of time on it. A proposition formula is in closed normal form or conjunctive normal form if it is a conjunction of disjunctions of literals, where a literal is either an atom or a negated atom. And this would be the standard way of writing that you know, with my sort of rare choice of symbols again. So this is A or B, and not A or C, and not B or C. And again, there are sometimes different ways of writing this down. So you might also see this set notation. So a closed normal form is written down as a list of lists or a set of sets, because the order doesn't matter, but a set of sets where we have A or A. So this is A or B, this is this one, not A or C, this is this one, or not B or C, so this is this one. So you might also encounter this notation, because this is what, when you write a computer program to do this reasoning, this is how you would represent it in the machine, and it's natural enough to use this way of representing things. And basically what you can show is that for every formula in propositional logic, you can apply a set of rules in a systematic way to translate the formula itself into an equivalent formula in closed normal form. And the rules that you can apply are rewrite rules, where you simply rewrite a formula P implies Q, whatever P and Q might be. So these stand for maybe complex formulae. And you rewrite it to the negation of P or Q. We all know this is equivalent because it's a definition of the implication operator. So that's easy. Once we've rewritten all the implications, we rewrite the statements where we have a negation outside a disjunction, a complex disjunction, and we do this by sort of multiplying the negation inside and turning around the operator in the middle. So negating P or Q gets not P and not Q, and the opposite for the conjunction. We have then to move the conjunctions outward. So if we have an R or P and Q, then we can write R or P and R or not Q, R or Q. And then at the end, we split the conjunctive clauses and rewrite in this way, or rewrite in the way that I've just shown you. And there should have been maybe a 0th line, and that is how to rewrite the equivalences. So an equivalence is rewritten into 2 implications in both directions. And if you apply these orders 1 to 4 or 0 to 4 exhaustively in this order, then you will end up in a formula with in closed normal form. So here's the example from the Wumpers world, where we had the information that there is a breathe in 1-1 if and only if there is a pit in 1-2, so the pit above or the pit on the right, 2-1. This is not in closed normal form, so we have to transform it into closed normal form by first eliminating the equivalence. We eliminate the equivalence by introducing 2 implications in one direction each. So we have B1 implies the disjunction, and we have the disjunction implies the B1 one. Yeah.
There's a mistake in the slide.
That is easily possible. Do you want to tell it now, or shall I get to it and stumble upon it?
I don't care.
Tell it.
It's the 3rd line, where you say move the negation inward.
Yeah.
The not P12. It should be not P12 and not.
Yes.
P1.
Yes. So this one is incorrect.
Yes.
Yeah. Okay. So let me go step by step, and then we end up at this mistake. So we have eliminated the equivalence. Now we eliminate the implication by rewriting it with the negation of the left-hand side or the right-hand side. So this is basically what has happened here. Then we have to do this negation inside, and this is where the mistake has happened, because we don't have we should have a conjunction here. And then basically at the end we have to apply the distributivity laws over conjunction over disjunction and flatten and get to this formula, which is in closed normal form now. And this is now something that you can input to your propositional logic reasoner, Davis-Putnam or resolution or whatever you apply, and then it can do reasoning over and can it tell you whether your formula is satisfiable or not.